Hey you guys, today we're gonna solve reactions on a beam, and I want to go over a few things before we start. I think I'm gonna have a total of about 3 or 4 examples, so feel free to skip ahead if you don't need this refresher, you just kind of want to look at the examples, but as always, I'll try to explain and then we'll work through the problems together. So, we have 3 types of supports typically. We have pin supports, roller supports, and fixed supports. Fixed supports resist forces in the vertical direction, and they also resist forces in the horizontal direction, as shown here. Roller supports only support forces in the vertical direction, and fixed supports support in the Y, the X, and they even support moments that are induced by some of the external loads on our beam. So I want to kind of expand on rollers and why they don't support the Y direction. How I like to think about it is, let's say, I guess I'll draw it up here. If I were to, let's say, I'm standing over here, and let's say I have a piece of, let's say, a large piece of plywood or something, just like that. I have wheels, and imagine there's some wheels like over here too. We can't see them. Let's say I'm here and I want to push this over. Well, if you can imagine, our plywood would just roll right off, and our rollers wouldn't really help us in that case. However, let's say instead of me pushing in this direction, let's say that I was actually standing on the plywood. Well, in that case, our rollers would be providing some reaction, and they would be supporting my weight as well as the self weight of the plywood. So that's kind of the same idea, and that's kind of the reason why we, in a theoretical sense, we want to include the reaction, the vertical reaction, and not the horizontal, because we can't expect the roller to sufficiently handle that horizontal force. It causes a stability issue. So that's kind of the reasoning behind that. But a lot of this comes down to static equilibrium as well. For our system to be truly balanced and for there to be no movement in our system, then that would mean that the sum of all forces in the X or the Y direction has to be equal to 0. And also our moments induced have to equal the moments, the reaction moments as well. So our system has to be balanced in that way. And you'll find that there's different types of loading conditions. These are 2 of the most common ones, but you might find others as well. But you might find concentrated loads. So here we have a pin and a roller, just a regular concentrated load, but we also might find pin roller with a uniform load as well. And we'll solve how to go through those. So first things first, let's denote the sign conventions. So I'm going to do up as positive, down as negative, to the right as positive, to the left as negative, and I'll do counterclockwise as positive, and clockwise as negative. You can choose the opposite of these, that's fine. But my only thing is you need to be consistent with the sign conventions, because let's say you mess up, then it's going to throw off your values and it's going to throw off your reactions. But yeah, let's start out by drawing our forces. So we have AY, AX. Of course, should have denoted this first, but I'm going to assume this is A, this is B, this would be our BY right here. As you know, these are our support reactions based on our support conditions. So now, let's apply some static equilibrium. So first I'm going to do forces. Sum of forces in the x direction should all equal 0. And that would be the case if this were balanced and there was truly static equilibrium, which there is, because this beam shouldn't be moving. So let's sum all the forces in the x direction. So we have the positive AX, and well, as you can see from the free body diagram, we don't have any other force that counteracts that reaction. So let's say, for example, that force was actually a value and there was no other force to counteract it, then that would mean this beam is moving. But we know this beam shouldn't be moving. We're in statics. So therefore, in order for this system to actually be in equilibrium, AX must be 0, because there's no other force. So 0. So we're good on that front. Now let's do sum of forces in the y direction. And I should have denoted this in my problem, but let's say P is equal to 10 kips. So when we do AY, so when we do sum of forces in the y direction, we want to do positive AY plus BY minus 10 kips is equal to 0. Now, we can simplify this a bit by doing AY plus BY is equal to 10 kips. We want to solve for the reactions individually. This is just an expression. So let's solve for moments and see if we have better luck. So one thing about moments is we can be pretty strategic with where we take it. So let's say we take it right at the point under the applied load. So that would mean that if we were to solve, let's just do that off to the side. So I'm going to call this point C. So if we take moments about C, it should equal 0. So if we take moments about C, I like to imagine I'm holding point C with my pen, and then I'm seeing how the other forces react to it. So, for example, this AY force right here is going to want to go like this about point C. So it's going to want to go clockwise. So I'm going to do negative AY because it's going clockwise. Then I want to do the lever arm to point C. So I want to do the 3 feet. Now, this BY about point C is going to want to go like this. It's going to want to rotate like that. It's going to bend like that. So in that case, it's going to be plus BY. Because it's going counterclockwise times 5 feet. And all that should equal to 0. Now, we wouldn't include this P because it's sitting right at point C. And if you think about it, there's no lever arm. So that term would just zero out. So we have two unknowns. We could solve for one of them and replace it here, but that's a lot more work. So what I want to do is, instead of taking moments about C, I want to take moments about, let's say, A. If I take moments about A, then the A cancels out the AY. You see that? There's no lever arm for it. So now, what I can do, let me erase these. So now, if I were to, we're taking about AY, right? So now let's look at this P. It's going to want to go like that, about AY. And that's counterclockwise. So we're going to do negative 10 kips. And then we want to do 3 feet. And then we want to do this. It's going to want to go like that, about point A. So it's going to go counterclockwise. Plus BY, and then plus the full lever arm to point A. So it's going to be 8 feet. So now you see we can solve for BY directly. Much easier. So if we solve for BY directly, we get 3.75 kips. Well, now we know BY. So now we can solve for AY. So AY is equal to 10 minus 3.75. Let's put units. So now we do that. That gives 6.25 kips, which makes sense. AY should be greater BY because the P, the force P, is closer to AY than it is to BY. So it should take more of the load. So that's how you solve that problem. Let's go to the next one. Looks like I kind of already solved it. Just go to this one. So here we have, let's draw our forces, AY, AX, and then we have, one draws a positive moment, a moment. Let's call it moment Z. So now, let's look for the forces. So sum of forces in the X is equal to 0. As we stated before, we have the AX, but there's no other force. So AX must be 0. Now for the sum of the forces in the Y direction, that's where it's different. So we have the positive AY minus the 20 kips equals 0. So AY must be equal to 20 kips. Yep, looks good. So now, I want to take moments about A. So if I take moments about A, we have that MZ reaction. It's positive because we're denoting this as counterclockwise as positive and clockwise is negative. So positive MZ, then we have minus 20 kips times the lever arm, which here let's assume 20 feet. So that means MZ is equal to 400 kip feet, which that would be our reaction. So our reactions are AY equals to 20 kips, AX is equal to 0 kips, and moment is equal to 400 kip feet.